Section 7-2, Operations on Decimals. Let's start by looking at how we add decimals. Now again, maybe we do remember how to add decimal numbers, but let's draw the connection between the rational number representation, fractions, and the decimal numbers. That way we can better understand why we do add decimals the way that we usually do. So the first thing I'm going to do is take each of the numbers that I want to add together. So 2 16/100ths plus 1 73/100ths. I'm going to write each one of those numbers in expanded form. The 1 to the right of the decimal is 1/10, and then the 6 to the right of the decimal is 6/100ths. And I'm adding that number to 1 7/10, added to 3/100ths. So I wrote each number in expanded form. I'm going to group together the like fractions. Now each number has a whole number part. I'll add those together. So 2 plus 1, combining the whole numbers. I'm going to add the tenths together. So I have 1/10 and 7/10. And then lastly, I'll add the hundredths together. We do that because it'll allow us to add the fractions more easily. So 2 plus 1, we have 3 for the whole number part, and then we have 8/10ths, and then we have 9/100ths. Now remember, to convert to a decimal, we can just look at the place value of each number. So 3 is the whole number. That will go to the left of the decimal. 8 is over the denominator 10, which means it goes in the tenths place. 9 is over the denominator 100, which means it goes in the hundredths place. So the sum of those two numbers, 2 16/100ths plus 1 73/100ths, it's 3 89/100ths. Another way that we can do this is to write each number as a fraction with a common denominator. So in this case, because we have 2 digits after the decimal, I'm going to pick a common denominator of 100. 2 16/100ths looks like 216 over 100. And then 1 73/100ths looks like 173 over 100. When we add those two together, we're really just adding like fractions. So we add 216 and 173 to get 383. Not 283, sorry, 389. And then we convert this into a decimal. So we've added our like fractions. Now we need to convert to a decimal. We know that 100 goes into 300 a total of 3 times. So we have 3 whole numbers. And then also we have 89 over 100. That looks like 89/100ths. So we get the same answer regardless of how we do it. But the connection that I want to show you is that essentially we are adding the digits that are in the same place value. So when we're adding 216 and we're adding, I'm sorry, not 216, 2 16/100ths, and we're adding that to 1 73/100ths, another way to do this, which is probably the way you're most familiar with, is to line up the corresponding place values. We're going to add the digits 6 and 3 because they're both in the hundredths place value. We get a 9. We're going to add together the digits 1 and 7 because they're in the tenths place value, so we get an 8 here. We're going to copy down our decimal so that we can preserve the place value each digit is in, and then we'll add the whole numbers in the one place. 2 plus 1 gives us 3. And the reason why we know we can do that is because when we converted these decimals into fractions, we saw that we were really adding the corresponding place values. Notice we added the ones, we added the tenths, we added the hundredths. And when we add like fractions, we're just adding the numerators, which happen to be the digits that are in each of those place values. So that's why we can use that standard algorithm that allows us to line up our numbers by aligning the place values. Typically we do that by lining up the decimal and then adding straight down all of the digits in the corresponding place values. Another way that we illustrated this was when we created fractions with the common denominator of 100. What we kind of did was added the numerators together as if they were regular whole numbers. Notice we don't have 2.16 in the numerator, we have what looks like 216. And since we know how to add whole numbers, we were able to add our numerator straight across, and then we considered the denominator afterwards. Now let's take a look at how we multiply decimals. And remember, we're not just looking for the shortcut of multiplying them, we're trying to understand why that shortcut works. So first, let's convert each of these decimals into fraction form. Since we spent an entire chapter working on fractions, we're pretty familiar with how to multiply fractions. So 4 and 62 hundredths turns into 4 and 62 hundredths, and we're multiplying that times 2 and 4 tenths. Now I'm going to turn these into improper fractions rather than mixed numbers. So I'll do 100 times 4 plus 62. That becomes 462 over 100. And I'm multiplying that fraction to 24 over 10. So I just converted both mixed numbers into improper fractions. Now I'm going to rewrite my denominators using exponential notation. So 462 over 100 will become 462 over 10 squared. And I'm multiplying that to 24 over 10 to the first power, technically. I'm going to multiply my numerator and my denominators. So 462 times 24 becomes 11,088. And my denominator becomes 10 to the third power. Multiplying 10 squared times 10 to the first, same base, different exponents. We add the exponents together to get 3. And now I'm going to convert to a decimal. The way that we can do this very quickly is to write out the numerator and then take a look at the denominator. It says 10 to the third power, which means the very last digit of my numerator needs to be 3 positions away from the decimal. So 1, 2, 3, the decimal would go here between the 1 and the 0. So our final answer would be 11 and 88 thousandths. Now notice that converting our decimals into fractions really allowed us to look at our decimal numbers as if they were whole numbers. When we multiplied our numerators, we used the numbers 462 and 24. And we could have multiplied those back in chapter 3 when we learned how to multiply whole numbers. So if we remember multiplying whole numbers, we kind of pivot. So 4 times 2 is 8, 6 times 4 is 24, carry the 2. 4 times 4 is 16, plus 2 is 18. Put a placeholder 0 so that we can pivot from the 2 in the tens place. 2 times 2 is 4, 2 times 6 is 12, carry the 1. 4 times 2 is 8, plus 1 is 9. And then we add vertically. So we have 8 plus 0 is 8, 4 and 4 is 8, 8 and 2 is 10, carry the 1, 9 plus 1 is 11. So when we multiplied these numbers, we could kind of say we ignored the decimal until the very end, which is where we say how many digits did we have to the right of the decimal before we multiplied. So going back to our original numbers, we have 2 digits from this number, 1 digit from this number. And we saw that when we multiplied by fractions, the 2 digits to the right of the decimal are denoted with a 10 squared in the denominator. And the 1 digit to the right of the denominator is denoted with 10 to the first power. When we multiplied those together, we found that there is 10 cubed, which suggests we need to have 3 digits to the right of the decimal in our final answer. So we start all the way at the right and we move in 3. So we get the same answer. And remember, the goal here is not simply to understand how to get the answer. The goal is to trust that that is the way to do it, that all of the math that we've learned up to now agrees with that process. It's not something independent on its own. It's actually just a neat way to organize all of the steps that we have to do. Now, this is a perfect time to talk about something called scientific notation. In science, you often deal with very large numbers and very small numbers. And at some point in time, our calculators couldn't handle these large numbers. And even that's true now. We have numbers that are so large that our typical handheld calculators cannot display all of the digits. So a way to get around that is to use something called scientific notation. Really similar to how we write our numbers in expanded form, except for what it does is it keeps the significant digits and then it writes that as a product of a power of 10. For example, I have on the left side of the screen 4 numbers that are written in scientific notation. The key is that you only get 1 digit to the left of the decimal every single time. So you will never have 2 digits to the left of the decimal in true scientific notation. Then you write all of the significant digits that follow in the number. So in this case, I have 2 significant digits, 8 and 3. The 8 is on the left side of the decimal, so it stays there. And then to the right of the decimal, I have only 1 digit, 3. When we multiply this out, basically what you would do is copy your 8.3 and then look at your power of 10. Where the decimal started, you're going to move that digit the exponent number of times. So in this case, our exponent is 8, so I'm going to move my decimal 1, 2, 3, 4, 5, 6, 7, 8. And because that's a positive number, I'm moving the decimal to the right so that my 8.3 grows into a much larger number. In fact, it grows into 830 million. So numbers like that are so large that we don't want to do math on 830 million, we write in scientific notation so it's more manageable. And we already know that if we multiplied something like 8.3 million times 1.2 tens of billions, I don't even, 10 to the 10 is not a number that I'm familiar with the name of. We could figure it out, but that's besides the point. If I wanted to multiply these two very large numbers, all I would have to do is multiply the significant digits portion, and then I would multiply the powers of 10. So if I did 8.3 times 1.2, now that we know how to multiply decimals, I would get 9.96 times 10 to the 18th power. That is a huge number. But could you imagine going through the multiplication process with 7 zeros in this number, 9 zeros in this number? That would be a lot of zeros to copy down. Scientific notation makes it much more concise. So the ins and outs of scientific notation. We already said a couple of them. One is that you will only have a single digit to the left of the decimal. 2, you will always multiply by a power of 10. It could be a positive exponent, it could be a negative exponent. So really big numbers have positive powers of 10. Really tiny numbers have negative powers of 10. If you have a negative number and you want to represent it in scientific notation, that is not a problem. You just tack on the negative out front, just like you would with any number that's negative. And that's about it. So that's pretty awesome. It's pretty straightforward. Let's practice taking some large and small numbers and rewriting them in scientific notation. Our first number. There's a lot of zeros here. these 3 zeros are unnecessary when we go into scientific notation. So remember, we're only allowed to have one digit to the left of the decimal. So I need to write my decimal after the 4. These 3 zeros on the right side of the decimal at the end of the numbers are not significant. They're not changing the value of our number, so I'm going to drop them. Then I need to multiply by a power of 10 that makes these two numbers equal. Now, the digits look similar, but notice that the decimal used to be all the way to the right, and I just moved it to be between the 4 and the 1, which means I moved the decimal 1, 2, 3, 4, 5, 6, 7, 8 times. In order to preserve the value of the number, I need this 10 to be raised to the appropriate exponent so that when I multiply this decimal 4.13682 times 10 to the power of 8, that I will get back the original large number. So let's test it out. If I were to move my decimal 8 times to the right, 1, 2, 3, 4, 5, 6, 7, 8, and fill in any zeros for placeholders, do I get my original number back? I sure do. So when you're doing scientific notation, the first thing you do is locate where the decimal needs to be, then copy down your digits, and then figure out what exponent your 10 should have so that when you multiply your decimal number to your power of 10, you get your original number back. Let's take a look at this next one. Here the decimal is between some zeros. In order to write this in scientific notation, I need a whole number between 0 and 1 to be in my ones place. So I need to move my decimal to be between the 2 and the 3. Then I need to multiply by a power of 10 that's going to preserve the value of that number. From the original position of the decimal to where I moved it, I moved 1, 2, 3, 4, 5 places. Now if I put 10 to the positive 5, that would suggest that when I multiply this that the number is going to get bigger. But we know that we had a very small decimal before, so it has to be -5. And the way that we test that out is we do 2.31, negative decimals go to the left. I have 5. That's where my new decimal would be, and then I fill in my zeros. And I can see that I have the same number that I started with. So remember, scientific notation is not changing the value of the number. It's very important that it preserves the value of the number. Let's keep going. 83 and 7/10. I need my decimal to be between the 8 and the 3 rather than between the 3 and the 7. Because I moved my decimal to the left once, what I need to do is multiply by a power of 10 that's going to move the decimal back to the right. Moving to the right at this point would be a positive 1. We need to move one place. So 83 and 7/10 in scientific notation would be 8.37 times 10. We don't have to say to the first power. We could just say times 10. Let's do one with a negative number. We have how many zeros here? 1, 2, 3, 4, 5, 6, 7 zeros. If I wanted my decimal to be in the correct place, it would need to be between the 1 and the 0. And then I need to multiply by a power of 10 that's going to move my decimal back to where it was. So we moved it 1, 2, 3, 4, 5, 6, 7 place values to the left. I want to move it back 7 place values to the right. So I'll put a positive 7 here. And notice that there was a negative in front of our number, so we'll copy that over as well. We have one last one, and it's tricky because at first glance you might think that's already in scientific notation, but nope, it's not, because the 0 cannot be in the ones place. And I feel like maybe I misspoke a moment ago. The ones place digit has to be greater than 1. So we can't have any digit here that is 0 or smaller. So we need to rewrite this so that it looks like 3.4, so that in our ones place we do have a digit that's greater than 1, and we're going to multiply by a power of 10 that preserves the value of the number. We moved our decimal once to the right, which means to preserve it, I would need to move it back once to the left. We already have 10 to the negative 6. I need to move it to the left one more time, which means it should be 10 to the negative 7. And we can confirm that, 3.4, if I move my decimal to the left 7 times, my decimal would be here. I'd have 6 zeros. 0.34 to the negative 6, I need to move my decimal 6 times. Again, I have 6 zeros, so those two values are equal. Scientific notation can be tricky if you first use it, so if you haven't used it before, take your time with these, practice them, double check your work, make sure that the values are the same. You can change the mode on your calculator to show your answers in scientific notation, so you can always type the number into your calculator and double check that it shows up the way that you think it should based on the process that we're using here to write scientific notation. You might notice that a calculator will write the number a little bit different. Instead of, for example, 4.13682 times 10 to the 8th, it might write it as 4.13682 capital E followed by an 8. And that's to say that it's being multiplied by 10 with an exponent of 8. So those notations are the same. By hand, we typically use the power of 10. On a calculator, we use E followed by the exponential value. Continuing on with our operations on decimals, we're now ready to talk about dividing decimals. Now there's a couple ways that we can do this. I'm going to show you two. First, we're going to convert both numbers to fraction notation. So if we're dividing 75 and 45 hundredths divided by 3, I'm going to write that as 7,545 over 100. And I'm going to divide that by 3, but if I write 3 as a fraction, that looks like 3 over 1. To do division with fractions, we know that you flip the divisor and then you multiply your two fractions. So this is great news. We're not really learning a new math operation here. All we have to do is take our decimal numbers, turn them into fractions, and then we're good to go because we already learned how to do this. Now when we multiply, I want to keep my denominator 100. So if at all possible, I should try to reduce the numerator with that factor of 3. We can check to see if 7,545 is divisible by 3 by using that shortcut divisibility rule that we know of. So add together 7, 5, 4, and 5. That would be 21. 21 is divisible by 3, which means that number is divisible by 3. I used my calculator to figure out what it was. It would be 2,515 times 3, which means we can divide off the 3's, and we can write this as 2,515 over 100. And then if we wanted to convert this into our decimal, we can copy down our numerator. Look at the denominator. It says that we're in the hundredths place, which means 2 digits after the decimal. So 25 and 15 hundredths. Another way of completing the division is to start off by writing your division problem using fraction notation. So I'm going to copy 75 and 45 hundredths into a numerator, and then 3 into the denominator. Now decimals inside of fractions, that's a little bit wild, so what we're going to do is multiply by powers of 10 to move the decimals to the right. Remember that we learned in scientific notation that positive powers of 10 move the decimals to the right. So if I do 75 and 45 hundredths multiplied by 10 squared, that'll move my decimal to the right twice. But if I do that to the top, I need to multiply the same value to the bottom to preserve the value of the fraction. This would then become 7,545 in our numerator over 3 times 10 squared in the denominator. At this point, I want to recognize that the goal would be to keep a denominator of 100 so that I can convert to a decimal easily. So I'm going to, again, try and reduce any factors in my denominator that are not powers of 10. In this case, it's the 3. We already did that earlier. We said 2,515 times 3 is the same as our numerator. Which means we can divide off the powers of the factors of 3. Then we'll try to convert this to a mixed number, so that would be 25 and 15 over 10 squared. We already have our denominator, that's simply a power of 10. Convert that to a decimal, 25 and 15 hundredths. So again, we get the same answer, it's just a different way to look at it. In one method, we converted both numbers into fractions and business as usual, same stuff we learned in the fraction chapter. On the other hand, we converted our division problem into fraction notation, multiplied our numerators and denominators up so that we could get rid of the decimals. And then we carried on dividing as if they were whole numbers. And that's actually the most common way to look at division with decimals. Multiplying by powers of 10 to eliminate the decimal. And because we know the fundamental law of fractions tells us that we can do this, that we're preserving the value of the fraction, we can multiply up by whatever power of 10 we want. For example, if I want to divide 13.196 by 0.13, maybe the first thing your instincts tell you to do is to write the division problem like long division. But dividing by a decimal on the outside, right here, the divisor being a decimal, this might make you just as crazy as doing division in base 7. Because trying to figure out how many 13 hundredths fit into 1, that's a little bit to wrap your mind around. So instead, what we're going to do is remember that this division problem can be written as a fraction. And then we're going to ask ourselves, what powers of 10 do we need to eliminate the decimals? On the denominator, I need to move the decimal twice. In the numerator, I need to move the decimal 3 times. If I just moved the decimal twice, the numerator would still have a decimal in it. So instead, we're going to move the decimal the greater number of times needed, which would be to the 3rd power. That way we can write our numerator as a whole number with no decimal in it. And the denominator would also be a whole number with no decimal in it. So what I'm saying is that dividing these two decimals will get you the exact same value as dividing these two whole numbers. So what we do, and we teach this to elementary students, is you're going to look at the divisor, and you need to move the decimal as many times as needed to eliminate the decimal in the divisor. We need to move it twice so that it becomes 13. However many times you move it in the divisor, you move that same number of times in the dividend. So then, instead of doing the decimal division, we're really looking at 13 going into 1316.9. And then when we divide here, we preserve the value by keeping the decimal lined up and then doing this like regular whole number division. So first we would ask ourselves how many times 13 goes into 1? It goes in 0 times. And then we say, okay, how many times does 13 go into 13? It goes in once. We subtract that off, bring down our 1. We already know 13 goes into 1 0 times, so we bring down our next digit so that we can ask how many times 13 goes into 16. It goes in once, subtract off our 13, we have 3 left over, bring down our 9. 13 goes into 39 3 times, and no remainder. So that decimal division gave us the answer of 101.3. And if you typed the decimals and the division symbol into your calculator, that should be the exact same answer you get. Oh, I've got a typo here. This should be 9 divided by 0.75. Now in this case, the divisor is 75 hundredths. The whole number that we're dividing, the dividend, is 9. Now 75, think of that as 75 hundredths, like 3/4 of money. 9 like 9 whole dollars. 75 cents is not bigger than $9. We know it's going to fit into there, but at first glance, it's not obvious how many times. What we need to do is move our decimal just like we did last time. Look at the divisor, so the number on the outside, and move the decimal as many times as needed to make that a whole number. We need to do the exact same thing with the dividend. So 9 has a decimal to the right of it to say it's a whole number. We need to move that decimal twice. Now there's no digits there, but we can fill them in with 0 placeholders. So now the division problem we're going to solve is 75 into 900, and that will have the same value as if we did 0.75 into 9. So from here, we do this as your standard long division. 75 does not fit into 9. 75 does fit into 90. It only fits in once, though. That leaves over 15. Bring down the 0. 75 goes into 150 twice with no remainder. Now the decimal is to the right of this last 0, and if I copy that up, that would go to the right of the 2. So our answer is 12, the whole number 12. The decimal is there, but we don't have to write the decimal if there's no digits that follow it. So we would just write the whole number 12 for our answer. As a teacher, you're going to hear this common complaint, when am I ever going to use this? Well, the truth is decimals are all over the place, mostly because money. Our money usually goes to 2 decimals. However, if you've ever noticed gasoline, they charge you 9/10 of a penny. So that actually goes 3 decimal places. But anyways, let's work on an application problem so that we can appreciate that these operations on decimals are useful. An owner of a gasoline station must collect a gasoline tax of 11 cents on each gallon of gasoline sold. So 11 hundredths of a dollar is 11 cents. One week, the owner paid $1,595 in taxes. That's just taxes, nothing else, just taxes. So if it's 11 cents for every gallon of gasoline, they had to sell quite a few gallons to bring that up to $1,595. The pump price of a gallon of gas that week was $3.35. Now the price per gallon is not changing the taxes here. 1 gallon is 11 cents flat rate. The reason why they tell us the price per gallon is for part 2. So part A says how many gallons of gas were sold during the week. So the way that we can think of that is let's break this down to a smaller problem. If they had sold 1 gallon, their tax bill would be 11 cents. Their tax bill was much bigger than 11 cents, so they must have sold more than 1 gallon. What if they sold 100 gallons? Then their tax bill would be the 11 cents times the 100 gallons that they sold. 0.11 times 100, that actually just turns into, whoops, 11. So that would be an $11 tax bill. So maybe they did like 1,000 gallons. If they did 1,000 gallons, then we would have 0.11 times 1,000. That would turn into $110. So they're selling more than 1,000 gallons, right? And we know that because we can see that if they sold 1,000 gallons, we would multiply 11 cents to each one of those gallons. That would be a tax bill of $110. So we're not even coming close to that. So instead of guessing like this, how about we figure out how many times 11 goes into 1,595? So we're going to do the 11 cents into 1,595. We know to multiply decimals, we need to move the digits of the decimal in the divisor so that we have a whole number on the outside. And if we move it there, we need to move it in the dividend. So my dividend now becomes 159,500. 11 goes into 15 once with 4 left over. 11 goes into 49 4 times with 5 left over. 11 goes into 55 5 times with nothing left over. So then I need to copy up my decimal place and fill in placeholder zeros. We just found out that the gas station must have sold 14,500 gallons of gas. And we could double check that, right? What if we did 14,500 gallons of gas? Then we would multiply the 11 cents to 14,500. And when we multiply that, oh, something's not right here. Well, maybe it is. Let's multiply it. We'll do 11 cents, so 0.11 times 14500. Oh yeah, that's it. 1,595. So we just double checked our work here. So to answer this question, 14,500 gallons were sold that week. Part 2, what was the revenue after taxes? Now, the pump price, this $3.35, that has to include the taxes, because this gas station owner is not going to sell you gas without passing on the tax to you. They're not going to eat the cost of taxes. So that $3.35, you could look at it as $3.24 is just the gas, and then the 11 cents is the tax. So the total price that you're paying at the pump includes the cost of the gas as well as the tax. So that would be $3.35 per gallon. We want to know what the revenue was after taxes. So first we need to find revenue. Revenue comes from how much you sold times the price you sold it for. So if we multiply the 14,500 times $3.35, we see that the revenue for the week was 48,575. But they want to know after taxes. So I'm now going to take that revenue and subtract the tax. So $48,575, and that is a whole number here, minus the tax, which was $1,595. That gives us 46,980. That's the revenue. Now, don't confuse revenue for profit here. Some of that revenue would have to go into maintaining the gas station, but we are removing the tax because the business owner doesn't get to use that tax money at all. They have to pass it on to the government. So here's an application problem where we used decimals, dividing decimals, multiplying decimals, understanding decimals in context of money.